I'm Andrew, and I'm here to share with you some results of the halfway point of a 4-season-long multi-site project funded by ISA. This work was really and is being led by Haiti Allen. She's a PhD student. She's the one that's making this all happen, so big credit to her. And then to our chief data scientist, Ezra. They're the ones crunching a lot of the large data sets that you're about to hear, especially greenhouse gases. So a bit of context for the project and then what I'll focus on in the next 40 or so minutes. This project is focused on understanding in a one-stop shop these different non-yield components that increasingly lots of soybean buyers care about. These are consumers, importers in places like Japan, South Korea, and the EU, where they want to know more about the soybeans from the US. What's the carbon footprint? What's the water quality, use, efficiency, or what's the water footprint? And then there's also questions that we get from our own producers on soil health. Things like, what's the best soil health test? Does it make sense economically to test for soil health by year 2, by year 3, following a cover crop? Things like this. So we're trying to understand once and for all across 3 different regions of the state answers to all these questions. We call this then, as a result, the benchmarking project, just giving benchmark data. Benchmarks are basically the minimum amount of data to inform decision making, and that's what we're hoping to do with this project. So we're halfway through, meaning we're 2 seasons in. That's 1 full crop rotation. We've got 2 types. And the basic questions that we want to answer in today's talk is, do we see responses that we would expect if we're doing things like no tillage versus cover cropping versus not? And specifically across these realms of water quality, soil health, and climate, or let's say carbon credits. Okay, so that's the overarching goal, is to understand this one-stop shop, how these things all connect. And the rationale, as I mentioned, is that there's increasing demand by consumers, but also by some producers on how do I get through things like soil health? What's the best way to measure soil health? I don't think that's going to be easy to answer. It's a tough concept to quantify. Great concept, difficult, tangible science concept. But we're here to try to navigate those soil health tests for producers. Second is to provide the basic data that the ISA can use to talk to potential buyers or future markets. Again, places like South Korea or Japan, the EU, they are increasingly placing a premium on things like the quality of the soybean, environmentally speaking. Third is to understand how soybeans can be used as a leverage point to improve water quality. Basically, corn is kind of a wimp when it comes to practices like cover cropping or no-till. We get yield drags that are appreciable. And soybeans are a bit more robust when it comes to those same practices that we know will deliver benefits to lower nutrient losses. So soybeans offer a way to enter into the crop rotation to decrease nitrate, decrease P losses. And fourth, and this I think has been less popular, but it's still there, it really exploded in 2020, carbon markets, both public, meaning the US government, USDA, but also now private sector. A lot of talk about carbon markets and carbon credits. We get lots of questions from farmers about, is $50 per ton of carbon reasonable? Is this promise of if you do cover crops going to pay for itself via the carbon credit? And so we don't really have great data to answer these questions across different conditions of soybean production in the state. So we're trying to give the basic data to benchmark answers and let ISA and farmers, agronomists, et cetera, do what they will with it. All right, so this project is based on, first of all, yields, that matters, and profitability. Haiti has shown some great data in past field days, like at Ewing this summer on the net dollar per acre. I'm not gonna focus on this, but I wanna point out that we are talking about these adjacent outcomes of interest for really consumers, and then for other stakeholders of ag. So soil health, water quality, and carbon credits are the ones that we'll focus on today, but the project itself is centered on crop productivity, profitability, but also weighing these. And the reason is that there are going to be trade-offs. So a bit more about the design of this project. So it's 4 cropping seasons, and we've got 3 different sites shown here. So we got set up in the Northwest on sable type soil, so the best of the best, up in Monmouth. We've got on campus, just south of us, about a quarter mile. And then we've got one down in Franklin County at Ewing Center. And so at each of these sites, we have corn, soybean, and we also began all these rotations in the soybean phase. So that way we can account for the inter-year effects and intra-year. So in some studies, if you go corn, soybean, but it's corn in year one, and then there's soybean in year two, you don't know if there's a change in yield response because of the weather or because it was the soybean or the corn phase. So we've got both phases present and so then at these sites on campus and down south, we've also got a corn double crop system where we double crop wheat with soybeans. That's not up north because from what I've heard, it's a little bit riskier to try that double crop, although I hear folks up in Kankakee are pulling it off, even up in Will County. So we've got 2 rotations, each phase of each rotation present each year. And then for each of these different combinations, we have 4 replicated treatments with 5 reps. And these are the full factorial combination of till by a chisel, and no-till with a cover or no cover crop. So we've got 4 treatments. These are pretty basic, but that's kind of the point that we're trying to benchmark these outcomes. It's hard to measure all the things if you have 25 treatments. So pretty simple design, but the value I think lies in the comprehensiveness of the outcomes and then in this geographic spread. So this is the design of the study. And to give you a sense of how much work this is and what keeps Haiti busy, and a team of technicians, there's about 5 other people that work on this, is across these sites we have 200 plots. If you do all the reps, all the sites, all the phases, so 200 plots total. And to measure soil health, we measure this at pre-plant and at after harvest. So that's twice a year, every 6 months. And we run a suite of soil health tests. We also do leaching. We estimate leaching with lysimeters. That's every 6 months. It's off season, so after harvest, before planting, and then in season. And then we've got the carbon credits, which is every week. Every single week, at minimum, we have to measure greenhouse gases. Soils emit gases. They're basically burping. They're exhaling. And to really measure carbon credits with confidence, which is not done by industry too much, you have to measure the greenhouse gas fluxes coming out. And that's weekly. So that's where a lot of the work comes down. And yields, of course, are yearly, or for the double crop wheat soybean system, well, twice a year. So that's the magnitude of this effort. Now, I mentioned trade-offs a couple of slides ago. One of the goals that we have as researchers is to do the high-risk stuff where we want to find out the bad trade-offs, where we get a lose-lose, where yields might go down and so do these outcomes of interest. And our job is to identify trade-offs where you might win one and lose on one. And then, of course, there's the win-wins, where you win on all accounts. And so you might think that there are some trade-offs in some of these different outcomes. Now, the net profitability depends. If buyers are offering a pretty high price per ton of carbon, it might be okay to suffer a 5-bushel yield drag if you make that up with a very high carbon price, for example. Same goes for soil health. If the eventual benefits of soil health to yield down the road outstrip the short-term post-adoption drags, so too that might play off. So these trade-offs are a function of time and of markets. They're pretty dynamic trade-offs. So they're going to depend by place as well. This is an example one, perhaps the most popular one that we hear about is that at $25 per ton of carbon, it doesn't really pay to do the practice to build that ton of carbon. In Australia, they're offering farmers about $150 USD per ton of carbon, $150. We're seeing numbers maybe 50 to 75 in most US-based private sector markets. So there's a big debate about doing cover crops or no tillage may not pay for the extra cost of things like cover crop seed, et cetera, but also maybe the yield drags in early adoption. So this is a example. As I'm sure that you all have, there are plenty of examples as well of folks using cover crops with great success and getting yield boosts as well. So I'm not ragging here on the cover crops. But the goal here again is the trade-offs. And again, these are going to depend on the region. And by region, I mean our 3 sites. If you're on lighter timber soils that are lower in SOM to start with, it stands to reason that you might be able to better build carbon sooner. That's what the science suggests. If you're up on sable soils in the Northwest region, those are so rich in carbon already, it is hard to build more carbon on top of that. That's the prime example of this trade-off favoring the south of the state, where you get maybe yield increases with covers or no-till, and carbon credits that are appreciable, but maybe not so up north. Again, these are examples or hypotheses. And it's also possible that we get wins across the board. There might be some combinations of tillage practices with cover cropping in some parts of the state where you can build soil health, decrease leaching of nitrate, build carbon in a way that's economic and not compromise yields, even increase them. So trade-offs don't always mean that there's a negative, but rather we have to see where there's lose-loses, lose-wins, and win-wins. All right. So our central question is this one in blue, is at this stage, 2 years in, halfway through, one full rotation through, can we detect differences in these outcomes? And today I'll focus on these 3 outcomes of interest: soil health, carbon credits, water quality, and we'll look at soil health from the perspective of 3 different kinds of tests of respiration, enzyme activities, which measure the biology, so to speak, and a new indicator that is quite novel, meaning it wasn't really in existence till about 8 years ago or so commercially, of active carbon. For carbon credits, we'll focus on the greenhouse gases. We are measuring organic carbon stocks, carbon sequestration, but as you probably all know, that takes time for manifestation. So we're going to wait till the end of the project to look at the carbon stock change. You cannot detect carbon changes in 1 or 2 years. And then for water, the focus is on nitrate leaching. We are looking at phosphorus leaching as well. But I'll focus on the nitrate leaching using lysimeters, which are basically a way that we can trap nitrate as it goes down the profile. Not as good as tile drains, but for plot work, we can't put in tiles to monitor them at the small scale. So it's the best we got. All right. I'll begin then with soil health. And again, the questions that we have are, can we detect changes in these outcomes halfway through, meaning 2 years into the project? Soil health. I'll begin with a bit of background here. So Dr. Zuber is an expert on soil health. She can probably tell you about this topic for hours, but I will give you a quick synopsis of how we're approaching it for this project. Soil health, we have 4 questions in this project. We won't talk about all of them today. First one that we will is, which soil health indicators, just what soil health tests, should we be using? Are they worth their money? They're not exactly cheap. My own belief is that a good agronomic test, look at STP, your pH, etc. Start with that, it's economic. Soil health tests are the dessert. Some of them may make sense, but whether they actually pay for their value, that's a different question. So what tests to use? Second is, when should we sample? And this is not just spring or fall, which we're testing, but also coming out of corn or coming out of soybean. So what is the right timing to capture what we think should be happening? So if we know that cover crops and no-till are good for soil health, it stands to reason that when we sample, meaning that we can pick up more differences in soil health tests, that would be the right time to pull those tests. So to put it differently, we can screen when to sample based upon these different treatments that we're testing. Third question we have for the project is, how do different practices in soybean crop production influence these outcomes? Seems kind of obvious, but not really good benchmark data. There's conflicting information. There's evidence that no-till can hurt soil health in some contexts, and some it's great. So we want to figure that out. And finally, I think the most important question is, maybe not so much but at what time scale, how long, and how much do healthier soils lead to more profitability, defined as probably less inputs and or more yield. So soil health itself is being defined by USDA NRCS as this intersection of chemical, physical, and biological, but really what makes soil health different from these predecessor concepts is the focus on biology. So prior to the 1960s, the concept that was in vogue was soil tilth. This was thanks to the Dust Bowl. And so tilth is more about a physical characteristic, right? The fluffiness. And that died out, as you can see from that graph. And then we see soil quality made this attempt to become the term by the 1990s. It kind of petered out, and we saw it outstripped by the soil health concept into today. And now there's official government programs with the title of soil health. So soil health is here to stay, unlike its predecessors that didn't really stick around. And it's being defined as being centrally defined by the biology. So we've got these new biological tests that set it apart from quality. So for that reason, we will focus on these biological tests today of soil health, and are they responding to treatment across sites by phase. There was a webinar that Haiti and I gave as part of the ISA webinar series. This is back in December 7th of 2023. And we walked through in a lot more detail, about soil health. And to put it to you, basically, there's two ways to conceptualize this. One, we know that soil health can benefit soybeans. There's 4 different mechanisms that we talked about, from the suppression of pathogens to end supply, which is a huge topic that we can talk about later. But also, it goes the other way. It's reciprocal. Soybeans can also be used to improve soil health. And as I mentioned, unlike corn, which is a bit wimpy when it comes to soil health practices in some cases, soybeans offer a leverage or an entry point in the rotation. You can do covers in front of soybean perhaps, but not corn. That's still better than not doing covers from a soil health perspective. And there's 3 different processes here that we'll talk about in the design. We're doing cover crops, tillage, as well as the double cropping evaluations. So think about if you're doing cover cropping in front of corn and then double cropping wheat and soybean, there are roots in the ground almost every month over those 24 months. And that's where there's very large benefits for lower leaching, but also soil health from that rotation system. Let's begin then with the data. So there's a lot here. I'm going to walk you through the slides. Just listen to what I'm talking about. Don't get too ahead of yourself with the figures. We're going to begin with respiration. So respiration is a measure of CO2. We're all exhaling CO2 right now. Most of what you exhale is CO2. You've consumed the oxygen. Soils, the microbes are exhaling CO2 all the time. You can measure that. And so the thought is that this is the measure of microbes being active. You're exhaling CO2 from some of the sugars that you ate at lunch, for example. And the rationale then is that more CO2 production would connote more labile carbon. Labile carbon simply means carbon that microbes can eat up. In other words, it's the basis of the food web. It's the energy source. It's the diesel for the microbes to do their magic. And this has many other names. Other different labs offer it in different ways or packages, from Haney to Solvita to CO2 burst, et cetera. It's all the same principle of measuring. You take a dry soil, you wet it up, and there's a burst of CO2. If you listen to it, it'll crackle and fizz a little bit because of the CO2 gases getting caught in the bubbles of water. So that's what we're measuring. All right, so this is thought to be the best indicator. Again, it's really measuring the biology, because the CO2 that's emitted upon re-wetting of a soil sample is made by the microbes. It's not a inert or non-living process. So what do we see? Nothing, to spare you all the details on the slide. Surprisingly. So what you're looking at here is we sampled coming out of the corn phase versus coming out of the soybean phase. That's the left versus the right column. And then you've got the 3 sites, Ewing down south, Monmouth in the northwest, and Urbana here on campus. And then you've got on the y-axis the magnitude, all on the same axis values. So if you see different treatments having the same letter shared, that's a stats way of showing that there's no difference. So these are all letter A's, which means that there's no difference statistically, and the values don't really oscillate very much. We see some things like there's more CO2 sometimes at Monmouth than at Urbana, but they're overall surprisingly similar, given that there's a big difference in total organic matter across these sites. So that was unexpected to us. And then you've got these different treatments where you go across the soil health gradient of treatments, where you go from covers with no-till on the left all the way to no cover and chisel-till on the right. Even down south where the chisel-till in Ewing is really not a great idea for those soil types and those slopes, but we're doing it. So across these gradients of soil health practices, after 2 full years, nothing is responding respiration-wise. So my takeaway here is that it's probably not a good soil health test to invest in. Any guesses what this costs at most labs, at most commercial labs, this test? Or if you know what it costs? 20? I've seen it as high as 45. Yeah. So pretty expensive, right? And there's not a whole lot of value, because we know that doing covers and no-till for 2 years is probably a good thing. You're double cropping wheat with soybean and with covers. You've got roots in the ground for 24 months of those 2 years versus not so much, maybe half of those months. And the respiration test is not picking up on that difference. So if we assume that this is the better soil health practice than this one, this is not the test for us. It's not worth the investment after 2 years. So note that point is that maybe after 2 more years, we'll see a difference. All right. So now we'll go on to these other biotic measurements of soil health. These are enzyme activities. So enzymes, just like what we have in our stomachs, in our cells, they break things down. They're a catalyst, so they expedite processes. And so soils have a metabolism, just like we do. In their case, these enzymes are secreted outside of cells. In our case, the enzymes are largely inside of our cells. But the point is that they do digestive functions, and they help unlock nutrients like nitrogen from this enzyme or phosphorus from this enzyme from organic matter form, which is not available to the crop, into forms that the crop can access, and microbes as well. These two are made by crops, and these are made by crops and by microbes alike. So crop roots also put these out, and then only the microbes make the carbon ones. So that's a bit of background here. This is just for the Ewing site, so I'll walk through the site in the phase of sampling for these enzymes. So we got 4 enzymes. These are the ones that USDA NRCS recommends for soil health testing, and lots of commercial labs offer these now. So at Ewing, sampling coming out of corn phase, we've got the 2 different crop rotations by color. We see that just one enzyme is responding, and it's responding within a given treatment of tillage and cover cropping to the rotation type. So this is what's called NAG. NAG, or chitinase, is N-acetyl glucosaminidase. It's just a fancy word for saying the enzyme that breaks down chitin. Chitin might sound familiar. It's what your nails have. It's what fungal cells have. So it's a measure of fungal-derived organic matter. The point is that people have found that it predicts very well a lot of nutrient cycling functions like carbon and nitrogen. So we see that in some cases at Ewing, coming out of corn, in this treatment, for example, of cover plus tillage, that depending on the crop rotation, you see higher NAG than not. And in this case specifically, full season soybean compared to the double cropped one, we see that there's about 50% more activity of this one enzyme. We don't see that for the other ones, not clear why. So kind of mixed sensitivity for this enzyme, right? It's not really picking up on treatment effects. So note that for a given crop rotation, so one color, we're seeing that they all have the same letter shared, right? They all shared that letter A. So it's not responding to treatment of tillage or cover cropping, but it is distinguishing the rotation types. Note this is in the corn phase. So the year's previous double crop wheat soybean is still carrying through the corn year through the fall, which is, I think, kind of impressive, that there's that lasting effect of the wheat and soybean roots in the ground for the previous year. Okay, now same exact site, Ewing, same 4 enzymes, but now it's the soybean phase. So these two are basically just saying, is there a phase effect? If you sample coming out of corn or coming out of soybean, do you see a difference? And the answer is that yes, we've got more sensitivity, more or less, through these enzymes if we sample coming out of soybean than coming out of corn. So there's one insight already, is that sampling coming out of soybean confers more sensitivity in these timber soils down south. And again, we see that it's the carbon implicated enzymes, but not the phosphorus and N enzymes that are responding. Now, this is a bit tricky because if you look more closely, we see that there's a lot of shared letters now. And so we see these differences by mixing rotation and tillage by cover crop treatments. What does that mean? So no longer do we see that for a given treatment of tillage and cover crop, a difference by rotation like we just saw, but rather if you combine these extremes of cover with till under the double crop compared to the full season with a different combination. So we have more sensitivity to the larger combination of rotation type, tillage type, and cover cropping. So overall, this isn't really satisfying to me, right? We're not picking up on a given rotation type, a strong tillage effect, a strong cover crop effect, and that's what we really want. The rotation being picked up on is nice, but I'd like to see more specific practice sensitivity. So that's Ewing. Note again that it's the carbon enzymes that are responding, not the N or the P. Urbana, I won't show you the data because it's the same as Ewing. By and large, we see the same 2 major trends, which is, number 1, we see that soybean phase sampling confers more sensitivity. So now we've got a mollisol site, these prairie soils, and the southern timber soil site. Sampling out of soybean gets you more differences by these enzyme assays. And second is that it's inconsistent by that soil health gradient. So if you go from covers and no-till to chisel with no cover, there's not a clear way of discerning what's going on with these enzyme assays. Any guesses how much these assays cost? One enzyme, what's the cost of the test? 35 per sample, per enzyme. So these are 4 enzymes, right? A little bit steep. Is it worth the money? I would vote no 2 years in for this site, for Ewing and for Urbana. Monmouth, so this is the high SOM site up north. There's only 1 rotation. We're not double cropping, so that's why there's just 1 color bar here. Same 4 enzymes again. And what we find here is that we do see what we would expect across the soil health gradient for the carbon enzyme in the top left. Meaning, if we're doing cover crops and no-till compared to no covers and chisel, we see higher versus lower activities. So at the highest organic matter site of Monmouth, we do see that this enzyme is sensitive to what we would be expecting for a soil health contrast between these 2 treatments. Okay, it's also though, like the previous sites that we just saw, it is only on the carbon enzyme. So we're seeing a lack of effects of tillage and cover cropping on nitrogen enzymes, which is interesting because cover crops immobilize quite a bit of nitrogen. You might think that they would impact end cycling, but it's not showing up with these enzyme tests. So that was the corn phase of Monmouth. We're going to switch to sampling out of the soybean phase. Recall again that we saw more sensitivity of these enzyme tests to the soybean phase than to the corn phase at our other 2 sites. But not so for Monmouth. It's exactly flipped. So we have more sensitivity at Monmouth sampling coming out of corn for soil health tests with enzymes. So this is the problem of it perhaps. It's hard to generalize when to sample phase-wise. So here what we find is that there's no response of any of our treatments or these enzymes in the soybean phase at Monmouth. Enzymes don't pick up on the soil health gradient of practices. Okay, and the phase effects, as we just saw, are opposite to those of Ewing. So you might be asking, well, why is this? We're working on it is the short answer. 2 things to maybe chew on would be there's a marked difference in these soil types. Monmouth are deep, lush soils, a lot of organic matter, black topsoil horizons that used to be up to 2 feet thick. Now they're a little bit thinner after 100 years of cropping. They're about a foot thick. But there's a lot more organic matter at Monmouth. That might explain why the carbon enzyme shows a different pattern. And it's also the opposite phase sensitivity than the lower SOM sites, central and south state. That might have to do with the amount of residues. So the phase effects, I think, could be root, but also the fact that there's roughly 3 times more residue, more tonnage of mass going onto a field as corn chewed up by the combine than after soybean. That's probably at play, but why it's opposite by site, that's unclear. So not really a strong argument for respiration or for these enzyme activity assays, at least not for what they're going for at $20 for respiration and $35 for enzymes. So let's go on to the final one for today, which is active carbon. Haiti's measuring other ones as well. We're not going to focus on those. POC, or active carbon, is a truly new test. We've been doing respiration and research for 30, 40 years. Enzyme since 1935, I believe, is the first paper. But this is really since 2003 that it was being advertised, I'll say, as a soil health metric. And it's being called an active carbon test. Active meaning microbes are presumably using this as a fuel source. So it's supposed to be like respiration, but even more sensitive. Same layout, we've got the 2 phases of sampling, left and right, the 3 sites, top to bottom, and the different crop rotations, etc. And what we find here is that at Urbana only, excuse me, that is a typo there. Yes, at Urbana only, at the southern panel, we see that there is a strong effect of the rotation type. So in the Urbana site on campus, we see that there's higher POX values in the full season soybean than in the double crop system. And that's pretty consistent regardless of coming out of that double crop soybean system or coming out of the corn phase a year after that system. So a bit like the NAG enzyme, that fungal one, we see a lasting legacy effect 1 year carrying through into the corn phase. So this is pretty strong, but it's only at Urbana. And again, it's not discriminating by the soil health practice combinations of tillage types and the cover cropping. So this is somewhat expected in the sense of it's not responsive to tillage or to cover crops, but it is to phase to the rotation, regardless of phase quite strongly. Let's talk about POC though. So this is a very popular test in circles. This I think goes, I've seen from as low as $15, 1.5, to as high as $25. Dr. Zuber confirms. Okay, so again, in that ballpark, if we're talking $20 per sample, I can tell you it costs our lab, this labor and the chemicals, about $3.50. It's pretty cheap to run. Of course, we're not in it for profit, but it seems a little bit pricey to me given what it costs. And it's also not really what we think it is. So if you'll bear with me here, I want to disabuse you of any myths about POC. So why the purple? Well, this is what permanganate looks like. Again, the POXC is permanganate oxidizable carbon. This is the stuff that you can use to disinfect water on a camping trip. The permanganate eats up organic matter. It oxidizes it. It makes it CO2. This has been used since the 1800s to get lignin out of coal. And it was proposed back in 2003 as a metric of active carbon because it correlates well with total organic matter. This was the rationale. And so there's been some studies like the ones here that if you're doing comparisons of, say, chisel tillage without compost versus compost with strip tillage, you get a higher value. Note the ppm. Just like a soil test P or soil test K value, it's the milligram per kilo, it's ppm. So this is an example of why people think it's sensitive to management. And second, it must be this very active fraction because it's a small percent, but it's an early indicator of eventual carbon change. That's a good thing if that works. That was the rationale. But I'll show you now two papers that are two of a string of 7 papers that we published with colleagues in USDA, pointing out that it's not what we think it is. There's still value in it. You can still pick up on, in this example, the effects of compost or tillage types, but it's not carbon and it's not labile. Here's why. So it's not labile because labile carbon should be easily digestible by microbes. So what we did is that we took different kinds of carbon. We took sugar, that's table sugar, sucrose. Microbes love that stuff. That's why your teeth rot if you eat too much. And we took things like lignin, what makes wood hard to decompose. And we found was that there's a higher positive value for pure lignin than for pure sugar. There's no way that this is microbial food sources if there's a higher score for the stuff that microbes always avoid, lignin, compared to sugar. Second point, and I'll skip through that, is that it's not even measurable as carbon. So this is a bit more chemistry deep to spare you all the pain of the redox chemistry. What we point out in this paper felt like cheating. I looked at my chemistry textbook, and if you do some math, the basic chemistry does not let you calculate the carbon. Long story short, there's assumptions that people were making in the 2000s that you can back calculate the carbon based upon the permanganate consumed. This is called stoichiometry, the ratios of these compounds. And what we point out is that depending on your assuming start point of the carbon in the soil, for the same exact value in the lab, you would get very different carbon values. We're talking by a factor of 250% differences. And the problem is that we can't know what the carbon values are in the soil at the start point, so we can't get the carbon value at the end point. That's a short way of trying to summarize a very long paper. So the point here is that basic chemistry tells us that we can't even calculate how much carbon is oxidized. So it's not labeled carbon or active, and it's not even a carbon test. But again, it tells us something. So we've seen from different studies, including on soybean systems, that this measurement does correlate in a positive fashion with higher yields of corn as well, not just soybean. It does respond to no tillage positively. So it's telling us something, but the researchers didn't do their homework in 2003, and they put out an unvetted test. So if you're being told that this is the active carbon test, it's not. Okay, I've said my piece. We will keep measuring it because, again, farmers are seeing in some systems responses. So I'm curious to know what this is. That's a different line of research. We will keep measuring it for this project, but just be aware that how you interpret it is a little bit questionable by the convention. All right, that's the soil health aspect. So far, there's no real salient soil health test that we found. Nothing really responded consistently across sites or across these different practices. That was kind of a disappointment, but being honest with you, that's what the research, that's what the data is showing. So it's probably not worth spending money on soil health tests 2 years in to a practice change. At least these tests are not going to pick up on many differences. Water quality, though, responds very quickly. So let's talk about that. This is nitrate leaching. We estimate this by lysimeters. We bury these about 2 feet down, and it traps nitrate that's moving downward. So is it as deep as a tile at 3 foot? Not quite, but it's the best that we can get without tiles in place at these sites. So we've got the same setup here. We've got the off-season and the in-season. So off-season would be after we take off the crop and before we plant. And then in-season is when the crop is growing. And a lot of folks just look at off-season, the brown gap of cropping systems. We think it's good to look at the full season of losses. And we've got our 3 sites here again. And this is the kilo event per hectare. Roughly, it's pound per acre, roughly. So this is going to be in the soybean crop year. And what we see here is that, this is a common theme, there's no consistent across-site effect of covers by tillage as that soil health gradient. But we are seeing effects of rotation and cover crops in some sites on nitrate leaching, as you'd expect. So what we see is that, surprisingly, when we're growing the wheat with the double crop here at Ewing and at Urbana, at Ewing we see that there's much higher nitrate leaching. The off-season would be when the wheat is growing. It's not really off-season for wheat. We think this is the N application that was made for the wheat that's being lost. It's about 10% of the application, roughly, is being leached. And then, but what's interesting is that in the ensuing soybean double crop, we find that there's lower nitrate leaching in the double crop soybean than in the full season soybean. So we get more nitrate leaching up front in the wheat phase of the double crop, but then less on the back end. The net outcome, though, is more net leaching when we double crop at Ewing over the past 2 years. At Urbana, we don't really see that as strongly. In fact, we see that there's more losses from the full season soybean. So it's a very southern state specific finding at this one site. Could be that these soils are very different. These are fragipan soils. The water sits high, perched on that fragipan. And I think there might be some funny business going on because with the fragipans, you tend to saturate soils more, and that favors more N losses. That's a speculation here, but something going on about soil types that's different at Ewing. Now, if we hone in here, that's what we just saw. Urbana is quite different. There's no difference in N leaching, regardless of whether you've got a cover crop in the off-season or a wheat crop. That was kind of a surprise to us. But it could be that we've got more organic matter. Look at how much higher those, look at the values of the nitrate loads. If we look at Urbana without a cover crop, it's about 12 or so pounds of N per acre. But at Ewing, without a cover crop, it's about 1 or 2. There's more organic matter at Urbana and at Monmouth, look at that, that can mineralize, make ammonium, nitrify to nitrate. So this is natural background organic matter becoming nitrate and being lost. These are the arguments for doing cover crops. Now, we don't see an effect, surprisingly, coming out of the soybean phase on nitrate leaching, but we do some cases for corn in season. So now we're going to switch out to the corn crop year. Now this is, again, the corn crop year versus the soybean year. You can kind of, if I go back and forth, you can see how things switch. And the first thing that comes to mind is that there's no clear effect of covers across all the sites, but we do see them in some sites. So the first observation here is that this is the corn following the previous year's double crop soybean. We still see higher losses at Ewing from that double crop soybean wheat. There's something about soybean and wheat double cropping in the southern side that is leading to more N losses. I don't think it's just the extra N that was put onto the wheat based on the magnitudes and the difference in time, but there's something there. And we also see again that there's higher losses if you have higher organic matter content. This is clear by Monmouth, right? We just see higher bars in general. So it's not that we're losing fertilizer N as the only source of nitrate leached. And the final point to make here is that the effects of these cover crops, which matter for the off-season, so if we compare the cover versus the no covers, not a strong difference here. We do see a little bit down at Ewing in some cases, but it's not very strong. So inconsistent results on this estimate of nitrate leaching. And that point's important as a caveat. These are estimates of leaching, not actual out-of-tiles leaching. All right, so now the final component of the project that we'll give you an update on is carbon credits. So there's 2 components to carbon credits. There's always the carbon in the soil and the carbon that leaves the soil. The carbon in the soil is the carbon stock. Carbon sequestration would be quantified as the change in the amount of carbon in your soil. Most assessments go maybe the top half meter, so 1.5 feet. We go down to 1.5 or so 4 to 5 foot. And we look at the carbon over a period of 3 to 4 years after a practice change. You will not detect a carbon stock change within a couple years. It takes time. Greenhouse gases, though, they're always being belched out every single minute. On a warm day like today, where it cracks above 0 Celsius, 32 Fahrenheit, you will see more greenhouse gases coming out compared to yesterday. And for greenhouse gases, we care about three major gases. There's carbon dioxide, CO2. There's methane, which we often think about rice paddies or cows being flatulent. And that's worth 84 times as much as CO2. This is how the climate responds to methane emissions. And so when we are weighing this in carbon credit programs, the carbon marketplace will count methane as 84 units of CO2. And the big one is N2O. So this is an N gas, nitrogen, from fertilizer or from organic matter. And that's almost 300 times the value of one CO2 unit. So a huge difference in this. And you want to quantify all three of these because a little bit of N2O goes a long way because it's worth so many CO2s. How do we quantify these? Well, the stocks, we look at deep soil stocks over the course of years. And for greenhouse gases, once to twice a week. If it rains, you have to go measure it because soils, if they get wet, then they belch. If they got tillage, they belch a lot more still. So it's pretty intensive. Most carbon marketplaces do not offer the greenhouse gas component because it's not cost effective. You can't have a guy out there taking greenhouse gases on your field every week for 3 years to monitor the credit. So people model, they estimate these. We want to actually measure what it would look like at close temporal resolution. All right, so a bit more about this. These are the units that we use. They're about 65K a pop. We have a small fleet of these that we deploy across the state because, again, every week, 200 plots across Illinois, we have to measure greenhouse gases. And being portable, they afford us a lot of flexibility. What we're doing is that we cap this piece of PVC and the gases build up. If you breathe into a bag, you can't breathe for too long, right? The O2 runs out. Same thing, we measure the change in the concentration once we cap that PVC collar with this headspace cap, and we can quantify these very trace amounts. We're talking part per billion for N2O and part per million for CO2. This is why it's really hard to measure. Now, greenhouse gases are the least measured portion of the carbon credit, as I mentioned, but they're also the most sensitive. So that's sort of the double-edged sword, that they vary a lot, but they also might give us a response within 2 years in a way that carbon stocks may not. That's why I'm focusing on this today. So here's what we have. Similar setup. This is last year's. I'm going to show you last year, so the year one, and then this past year, 2024. This was a pretty dry year, right? It was the third dry summer through July, I think, in recorded history of Illinois of 137 years. And to break this down, we've got the three different crop rotations, if applicable, not for Monmouth, for the double crop. We've got the corn phase, the soybean phase of the corn soybean, and then the double crop one. And then you've got the three different gases. We care about CO2, about the N2O, and about the methane. And this is the CO2 equivalency. So we are accounting for the fact that the CH4, the methane, is worth 84 units of CO2, et cetera. So the total bar height is the total carbon credit, kind of, because it's the difference among the practices that's the credit. Meaning, if you're doing chisel till and no cover on the right, versus if you were to adopt this one here, so the no cover, excuse me, I messed that up, folks. If you're doing chisel tillage and no cover right here, and you go to the no-till here, that would be the difference. So that's actually a negative carbon credit, right? You get more CO2 emissions going from this one to that one. That happens sometimes. Sometimes we see gases increase with no-till, increase with the cover crops. So it's a difference among these bars that you want to think of as the potential credit that a marketplace or a carbon program would be paying you for. It's the avoided emissions. So a lot of data here, but to walk you through, we're looking at these as equivalency, and they're driven by CO2. The blue bar is the biggest bar. So most of our equivalency of the carbon credit then is going to be CO2 based, followed by N2O. Methane is very trace. We do see these in these prairie potholes that are very wet. Those wet spots are just belching up methane. That's why rice paddies do the same. It's submerged soil. But by and large, it's CO2, it's N2O in this part of the world. First thing to note is that we see, we see a difference by sites. They tend to be a little bit lower at Monmouth proportionally in terms of the source. And this might again point to the effects of the differences in soil types and the hydrology. But by and large, if we look again for those letters, we don't really see a whole lot going on. We just see at Ewing and at Urbana different letters, meaning that there's a difference depending on the phase, the rotation, and then these different treatments. And so if we've got cover with chisel till here, we've got higher emissions compared to these ones with A, which would be cover with no till. So that right there, if you compare these two treatments at Urbana, this mitigation, you're going from roughly 8,000 pounds per hectare of carbon equivalent. By going from chisel to no-till, you're going down to about 6,000. That's about a 2,000 pounds, so 1 short ton of carbon credit in this site in this year by adopting no-till, as an example of how to read this. But it's inconsistent, right? We don't always see this same trend of it is going to be lower with no-till compared to till, or lower with the cover crop. This kind of makes sense. The cover crop is going to decompose. It's going to be giving off that carbon. So sometimes we see CO2 go up with the cover crop, not go down. It's the no-till that tends to afford more mitigation of greenhouse gases in some cases. So what's the takeaway? When these greenhouse gases differ by these soil health treatments, they tend to be lower for no tillage. But the when is a big when, because it's a very inconsistent when we see that response. So that was last year. Now we see this past year that we had, which is a more quote-unquote normal year. It wasn't the third dry summer in recorded history. And when you have less water, microbes are less active. So we thought that we would see more greenhouse gases this past year versus 2023, and it was the opposite. That was a little bit unexpected. In any case, we see overall similar trends. So when greenhouse gases differed, they were higher for tillage, chisel tillage, compared to no tillage. So that's at least a consistent pattern that we're seeing in this project across sites. We see again that Monmouth does not respond in terms of its greenhouse gas emissions. And note the huge difference by sites in this year compared to last year. So, in 2023, all sites were pretty high. Last year, though, we're almost having a 2 to 3x difference by sites, a lot higher down at Ewing. Those fragipans on which the water table is perched, that sits in wetness, you make a lot more N2O. And look at the N2O in green, a lot higher values at Ewing compared to Urbana, even though there's a lot more nitrogen in the system by virtue of higher organic matter at Urbana. So this is a good point that it's the hydrology and the organic matter plus the N inputs that together determine the amount of N2O being emitted. So a little bit unexpected, but can be explained. I want to focus in on this last year to look at Ewing for a couple of treatments just to show you what this would look like and to ask the question, does this pay for itself? Does a practice being adopted pay for the carbon credit based upon current pricings? So in this one system, this is the double crop system at Ewing last year. If we compare these two treatments of no cover with till versus no cover with no till, that's basically a no cover comparing tillage effects. And that difference there is about the emissions that you would avert. So by switching from chisel to no-till, you decrease the total CO2. That would be about 1,300 kilos of carbon per hectare. It's about 1,200 pounds of carbon per acre, roughly speaking. So that's about 0.6 ton of carbon. You often hear of these carbon credit programs promising that you'll get payments if you do a switch to no-till of $50 based upon $50 per ton, assuming 1 ton per acre per year. I could talk about why there's a lot of issues with this. You don't just build carbon indefinitely in soils, they saturate. If you begin with more carbon or you've been doing no-till already, there's this effect of the past practice. But the point is that would be, if you're assuming $50 per ton, 0.6 times 50 is what, $30? It's about a $30 per acre credit, assuming $50 per ton of carbon. And that would be in this 1 year that we saw at this one site. So it's hard to predict. And if you get audited as part of a carbon credit program, this may not hold up in all years. So my point here is that the carbon credits that we can gain from these practices are very site dependent. They're hard to broadly claim, and that they may not really be paying for the extra yield drag or the extra costs in the case of the covered crop. Now, they may have benefits from a crop production and soil health perspective, but the carbon payments, I don't think that they're really high enough to offset the risk. That's my own opinion from this. Again, we're in the second year. This is the greenhouse gas perspective. I think we'll see with more confidence by the end of 4 years, both the organic carbon in the soil and the cumulative greenhouse gases over 4 years, what the outcomes are. All right, so I think we're getting close to time. I'll skip through the N2O slides. My main point to make was this first bullet point, is that N2O, agronomically, I could care less about N2O, but I care about it insofar as carbon credit programs care about it and are making payments specifically on N2O. You are going to hear more about N2O. It is in the crosshairs of the USDA as the greenhouse gas. Remember, it's 300 units worth of CO2, and the thinking goes that because some of this N2O comes from fertilizer N, we can manage this more than the CO2 component of the total greenhouse gas pie. I'm not sure that I agree with that logic. That's what the USDA is claiming. And the point is that a very small amount of N, 2 to 8 pounds, is what we see across these last 2 years, all these plots. That ends up being quite a bit of carbon equivalency. So stay tuned on this, but the slides were just pointing out that the N2O is not all just from the fertilizer, because unfertilized soybean emits as much as fertilized corn in some years. So the N2O is not from the fertilizer, it's coming from organic matter, just like we see for the nitrate leaching. That was the takeaway of these slides. So in the interest of time, I'm going to end on this slide before I summarize this. So I want to point out that ISA made a big investment for which we're quite ingratiated, and we've tried to leverage that investment. So it's good to bring in outside dollars from the feds or from outside groups for every dollar invested by ISA, which is coming from producers. And so to give you a flavor of this, we've been able to use these sites that we've established with ISA funds to bring in one project from US Soybean Board for $360K. We were able to bring in one from the Salk Institute. This is out of California. They're breeding high-yielding soybeans with roots that decompose more slowly. And the thinking is that that might be a way to sequester more carbon in the soybean phase. If the roots are modified to not decompose as quickly, then the carbon will stick around for longer. So that one is 1.2. We used the same exact sites we think we have this locked in, a larger project of 6.2 from the company that makes Ozempic. I'm sure you've heard about Ozempic. They are flush with cash, and being Danish, the Danish passed the first carbon tax in the world, in effect in January. They tax you on every single thing, from food to gasoline, for the carbon emissions. And being Danish, and this is a company from that country, they want to invest their profits from Ozempic into climate smart agriculture. And so they've approached us, and we're working on locking this down. And the ISA investment that we could point to as data on N2O is what got them on, because they care only about N2O. What I was saying before, this is the new greenhouse gas in the crosshairs. And finally, we have a side project that's going to begin at the alma mater plots. This is the Morrow Plots 2.0. This is a 70-acre tile drain study on the South Farms. And this is about $500K that we brought in to look at N2O emissions from the soybean phase specifically. And what we think is that the EPA is overestimating how much N2O comes from fertilizer, because they think that it's all from fertilizer. That's an assumption that has to be tested. And we know that soybeans are responsible for part of the N2O emission across the 2-year corn-soybean crop rotation. But unlike the corn, the soybean gives you a chance to try to manage that N2O. So soybeans have a step up, I think, over corn phase when it comes to tamping down on the N2O emissions through things like cover cropping. So I point this out because we've 10x the investment by ISA, and we will try to keep on doing this. It helps us bring in dollars that are not being paid by the farmers of Illinois. These are paid by Ozempic users, by Californians, thank you very much, and by US Soybean Board, so still some farmer input. All right, to summarize all this, we're halfway through this 3-site, 200 plots measured every week for greenhouse gases project, looking at soil health, carbon credits, and water quality outcomes. And I've shown you just a snippet of this is maybe 1/5 of what Haiti is working on, but these are what we think are the best takeaways to date. The overall summarization here is that no soil health tests out there that's biologically based is responding consistently after 2 years. Is it worth the $35 to $40? Probably not. In 4 years, maybe it will be. We're not sure yet. Second is that respiration was the least responsive. Perhaps the most popular one out there on the market, it was not responding at all. I think enzymes are a better bet than respiration. And POC-C kind of responds to rotation at Urbana only, but it's not active carbon. So we were trying to figure out what this thing is. Third, nitrate leaching is responding. It responds to the SOM content of the site. Higher SOM will lead to more leaching, which points again to the need for things like cover crops to decrease that. But we did not see a strong effect of double crops. And we saw this unfortunate increase in leaching with double crops, wheat and soybeans, which we think again is from the N being put on the wheat. And finally, we saw that at most we get 3/4 of 1 ton of carbon per acre by mitigating the greenhouse gas emissions, largely by going from chisel to no-till, but that depended on the site and on the year, and it was really inconsistent. So overall, after one crop rotation, 2 years, there's not a whole lot responding right away. So a really high-level takeaway is patience. These tests, these carbon marketplaces, being commercialized as early response measurements or programs, the data does not really support those working right away. It might take 4 years, we'll find out soon. Alrighty, that's all that I have. Happy to answer any questions, and thanks for your time. Yes, sir.
Does private industry care about your findings? I mean, because I imagine all these programs are going into the system based on modeling.
They are.
Is that right?
There's largely select soil sampling. They'll pull maybe a 12-inch soil core, and there's a lot of modeling going on. But the greenhouse gases, they'll, I think, use a few trials, and then they'll extrapolate across the entire corn belt or the entire state.
So it's conceivable that the models will give more credit than what actually happens based on your research?
By credit, you mean there's more weight placed on them, or?
I mean, more than like 0.75 tons per acre, I don't think pays any bills, kind of, as well.
Sure. From the numbers that I've seen, I think that there's a lot of overpromising going on.
That's kind of what I'm
Yeah,
Is private industry paying attention? I mean, is there a lot of this experimentation going on in the agricultural world? I mean, is private industry, is this going to like shrink the whole carbon market thing to the farmer?
from this study alone that ISA funded?
Yeah.
I don't think so. Here's how I see it. We've known that a lot of these practices cannot give you carbon credits as more carbon sequestered or less gases emitted. This has been known since before I was born. This is a 1970s, 1980s finding. The companies kind of sidestepped that. And a lot of the scientific community, at least the folks that I work with, this is kind of a known fact that you cannot realize 1 to 2 tons of carbon per acre per year by adopting to no-till. I think if you've got extreme degradation of soils, if you've been hammering moldboard on a hilly part of the south of the state and you go to cover crops and no-till, then probably you get massive gains. But in terms of the status quo of it's corn, soybean, it's being well managed like most farms are across the state, you're not going to see 1 ton per acre per year every year. And that's not our data. That's, I think, the literature for the last 30, 40 years. So why are the companies doing what they're doing? There's a lot of investment money being poured into this. And this is out of my league here perhaps, but they're kind of too big to fail with all this VC money being pumped in. So the thought is that it's a bubble. They're going to make it private sector, and they need the feds to give carbon an artificial price, and then you can capitalize on it. And if the bubble bursts, well, they're going to pull out in time. That's the pessimistic view that I've heard from my friends in industry. I'm just a researcher, so I can't speak to that. I'm curious, are folks playing around with carbon marketplaces? Because I've heard that there are some good deals out there. I just haven't really seen any myself. Okay, yeah. In Australia, they're doing it really well. They're paying a lot per carbon ton.
What's the difference?
I don't know. I think that one is that
Is the European market higher than America?
I don't know. That's a good question. I think it's higher. It's not hard to beat what we're seeing here. We got really low prices compared to the rest of the world, but I think Australia, they've got a group called Cicero. It's the USDA version of Australia, but it does all ag and livestock research. They've been working on this since the 80s, and they've found that what it would actually cost to build that carbon is going to be upwards of $150, $250 per ton. So I think they're listening, their companies, to their scientists. But I'm speculating.
So you're saying with the 150 to 250 per ton, it's going to take more to raise that, so that all those additional dollars are going to get eaten up with all the additional practice changes. Am I hearing hearing that right?
You mind repeating the question, please?
Not that a question, it's much of a statement.
Oh, sure.
So they're paying $150 per ton, but it sounds like, and like I said, maybe I misunderstood you, but it's taking more for them. They feel like there's a lot more involved to hit the carbon levels that's higher than what we're achieving here.
Great question. Yeah, there's two things here. One is how much carbon can you build? The other is how much do we pay for that carbon, right? So per ton basis, just how much is it worth? The Australians think that to build any amount, it's just going to cost more than what the US private marketplace, investor base, thinks it takes. So VCs here are saying, 30 to 50, maybe $80 a ton. Australia's saying, no, it costs like 100 plus, maybe more like 150 per ton. Separate from that is how quickly and how much can you build the carbon? And that's agnostic to the country. That's just how soils operate. I think that we're way overestimating. But if you're getting $200 a ton, building half a ton per acre is actually not too bad a deal now, right? And so that's where the pricing goes hand in hand with the, I think, realistically more sober, lower amount that can be built up. Does that get at your question?
Yeah.
Cool. Yeah. All right. Well, thanks very much.